let's continue on. The IPC is sort of interesting, right? In terms of speed. So if we look, for instance, at pipes, for example, you've got quite a few crossings from user space to kernel space and back and forth. Okay? You've got to do a write, and then on the other side, you've got to do a read. And so what the Aegis, this XO kernel, does is tries to streamline IPC. Right? The idea is if you could build something fast but very simple, it's possible to build something more sophisticated on top of that that suits your needs. So what happens is you can actually call yield and then directly specify a process to go to. Okay, so you say yield a PID, and that will then, right, go into the kernel. Oh, there's a better one. And then the kernel will send that to, so this is process 1, and this is process 2. And so we say basically here yield 2. That will then go via an upcall into process 2. Okay? So it's almost directly just sort of jumping to a location in process 2. Okay, there's only certain approved locations, kind of like you have a system call or an interrupt table and so on that tells you, or a trap table telling you where to go. There's a similar idea kind of here, that there's a few well-known locations. So it goes into, and I'm not sure whether you pass one of those locations or not, but it goes into here, and then process 2 gets to do what it wants with it. So, you know, handle yield, perhaps, is what we'll call it. Okay. And what about the data to be passed? Well, all it really passes is whatever the registers are. So whatever the registers are here, we hop into the kernel, we change the page table, if we have a page table, otherwise we flush the TLB, and then we go into handle yield here. And handle yield now has access to the registers. I believe one thing it does get, so one of the registers is set to the no, even that's not true. We don't have to have a requirement. So what handle yield can do is do what it wants. If it wants to communicate back, how would it do that? Yeah, so what it could do is yield. It could do some computation of some sort and then yield back to process 1. How does it know one's process ID? It must have been in a register. So here, this maintains registers. And so these guys can kind of agree, okay, I'm going to go ahead and put in AX the PID that is sending. So the operating system is agnostic as to the understanding of what data is being communicated. All it does is maintain registers. Does that make sense? Yeah.
In our operating system, or in JAWS, we also have the ability not just to pass values, but also like pages.
Yep.
How would that be supported in this?
You would have to have something very similar to syspage where you can set up a mapping into another process. Yeah, and that way makes sense because if you've got large amounts of data to pass back and forth, this prevents having to copy it from buffer to buffer.
How does that work if you're like using a language
you'll have to get some help from assembly. You know, you have to write a little bit of assembly glue code for that. Okay. I mean, and it's only via some special extensions to GCC that allows us to actually put stuff into and out of registers, right? Basically with the asym directive. Other questions? Okay. You can see the approach here really is do the minimal amount possible and just get out of the way and dictate as little as possible. And then we've got this speed on top of it. I'm going to skip that. And let's see. We were talking over some of these questions on Monday. The multiplexing and packet filters. So we discussed that on Monday. Do people still have questions about that? Is it fuzzy? Basically, again, it's a little language that you were using, a custom-defined language for which there is, in some cases, there can be an interpreter. In the case of the paper, they actually dynamically generate code to inspect packets, look at the values, do some computation, and then decide either whether it's their packet, or I think they actually have the ability to send a packet in response as well, so that you can have an incoming packet cause a return packet without actually ever going back into user space. By allowing apps to manage VM, et cetera, can't that potentially cause high workloads on the kernel, slowing down OS performance? I guess in the sense that you can have user code that's handling page faults, and that user code can be as slow as the application developer wrote it, as opposed to, let's say, the operating system, where they see the code, they know what it is, they can control it. On the other hand, as long as we just I guess the way I would say it is an application could be penalized by being slow if it's written poorly. That's true no matter whether it's doing its own VM or not doing its own VM. So this is just another opportunity we give it to do it poorly. If you look at the worst case, the dark cloud part of it. The silver lining part is if they write it well, then they can get lots of advantages. The dynamic packet filters, there has to be some trust here in the dynamic packet filters, in that we have to some idea of who's allowed to install the dynamic packet handler, what they're actually allowed to access. And also we want to ensure that the packet handlers don't overlap one another in terms of the packets they want to handle. Okay, that we can handle with some static analysis. Applications have more authority and responsibility with an exokernel. Are there disadvantages and loopholes where malicious apps can do harm to the kernel? No, not if it's properly written. And the nice thing is the surface area often is fairly small, right? It doesn't provide a lot of functionality that another operating system might provide, and that functionality usually leads to possible security holes. So if it's written correctly, no. The bind time and access time authorization is really just when do you check to see what your privileges are, okay? Whether you're allowed to do something. Do you check when you're setting it up, or do you check when they actually do access? So if we imagine access of memory, if we wanted to check sort of on every memory access to see whether someone is allowed to access that page, that would be, well, not only slow, but difficult, because without hardware support, unless you're interpreting or something, there's no real way to do that. So the setting up a page mapping is an example of bind time authorization. We check at the time they set up the mapping whether they're allowed to do it, and then we just let the hardware control that. Microkernel we talked about. The end-to-end argument. I'm not going to get into that right now, or the others. The resource revocations and aborts, we talked a little bit about that. cases where an exokernel would not be preferred, yeah, if you like the functionality that, let's say, Linux provides, use Linux. But you're not going to gain much from using an exokernel. And you can now, your choices really would be it was close. So your choices are use some sort of a POSIX kernel. Like, give me 3. Linux.
BSD. Technically, Windows has a POSIX layer.
I just feel so bad about writing that down. Yeah, Mac OS, which is Mach plus BS. It's Darwin, actually, right, is their version. So we'll put that. OK, so you can use a POSIX kernel. The other alternative, if you're not going to be using the exokernel facilities in your application, would be to run your app plus, let's say, a POSIX libOS on top of an exokernel. Right. And if you're not going to use any of the facilities, I don't see there's an advantage to that particularly. What things are there you could do on top of a monolithic kernel that you can't do on top of exokernel plus libOS? Well, we haven't actually talked about, so what happens if we got our exokernel here, and we've got our app plus our POSIX libOS, and then we've got app2 over here plus the POSIX libOS. So they're both running on top of our exokernel. What if these guys want to communicate with each other? Can they? How? Well, they could use the exokernel facilities. Can they use the POSIX facilities? So if well, we know one way, I guess, that was talked about on Monday, which is I can send TCP/IP packets right back and forth. That's one way I could do communication back and forth. But can I set up, for instance, pipes between these? Probably not. I guess that's true. You could have an OS here, a libOS, that will allow communication with other libOSs. One problem you have to keep in mind is this libOS can afford not to trust this application. Okay? Because if this application screws something up, the worst it could do is ruin this application. Right? But if you're now communicating with other apps, there is some question of whether you can't necessarily trust this guy because we don't know what he's done. So one would have to. So IPC between apps, between processes, is simpler on a monolithic kernel than it would be on an exokernel with these separate libOSs.
How do you make a file system with permissions on an exokernel that multiple apps are allowed to?
Yes, that's a good question. And I don't know the answer right now. I will think about that. And, yeah, I won't think about it now, though. Okay, so Biscuit. I don't know how people come up with these names. So we've got, in general, most kernels are written in C. And a reason for that is C gives programmers total control. Why does it give programmers total control? Well, C has been described as portable assembly.
It's a bit nicer.
Yeah, it actually is nicer. We have loops and we have things like that. But it is low level, and part of the reason it was low level is because it was designed in order to be this implementation language for Unix. And so we need things like twiddling bits. By that, I mean something like, XOR and, or, and so on. You look at a language like Pascal, which is about the same from about the same time frame, and that doesn't have any built-in facilities for doing and or and so on. You need to be able to have control over memory layout. So you want to know, for instance, if you create a structure with some fields in it, that those will match, let's say, the fields associated with the hardware that you're actually communicating with. Okay? You need, or what works well, I guess, is having pointer arithmetic. And being able to just do lots of stuff with pointers and be able to indirect via pointer to wherever you want in memory. So that's why it's useful to be able to say something like, you know, int star x equals ox f00000, and then do something like star x equals, you know, 1, 2, 3. So I can write to a particular memory location for memory map.net. It turns out C is hard to use correctly, sort of like assembly is hard to use correctly too. Right, you are given a gun and they're perfectly happy to let you shoot your foot off if you want, right? The memory management is one example that is often gotten wrong. So let's look at two common problems. Buffer overflow. How many people have heard of buffer overflow problems? Secure, yes. And give me a language that has buffer overflow problems. C, good example. Yes, because there's no checking. Give me an example of a program of a language that doesn't.
Rust, I think.
Rust, I think. Java is a great example, right? You try and access an array, and if you go out of bounds, it doesn't blindly give you whatever happens to be there. You get a runtime exception. Pascal, which I was talking about, is from about the same time frame as C, actually does have the option of doing runtime checking. So the system programming language for the Mac used to be Pascal. That's how you would write Mac programs. And I say system programming language, that's not quite true. The system itself was written in assembly, but your interface was via Pascal. And so I had a friend, we used to, you know, write Mac programs, and there was a facility that by default, the Pascal compiler, when you ran, had bounds checking. Okay, and I don't remember exactly what error, the error that you got was not as nice as in Java, where it tells you, you know, what the index is that's bad, for example. But you would get a runtime error if you tried to overwrite your bounds. And then there was an option to disable that. Every shipping program disabled that because they didn't want to pay the overhead. Okay? And so my friend, who he was actually a mudder, he said, it's a lot like if you were doing shipbuilding. And in dry dock, you'd have all your lifeboats carefully on the ship. But as soon as you actually set out to sea to go across the Atlantic or something, you left the lifeboats on the shore because you didn't want to pay the weight. Okay. So that's how I always think of buffer overflowing and checking. Use after free, right? The problem is we have in C, you know, we've got to do a malloc somewhere. This is in user code, right? We do a malloc, and then sometime later we free. Okay? And there are a lot of things we can get wrong. We could malloc and fail to free. We can malloc and free twice. We can malloc and free and then use it. Right? All not very good. And C does nothing in particular to help us with this. In the kernel, we don't use malloc. Right? We use probably our own version called something like calloc. Right? Kernel alloc. Because we don't have the same underlying access to memory. Right? If you're a process and you allocate more memory, you call sbreak. to get more memory, and we don't have that option in the kernel. So we'll pre-allocate some memory usually, and then parcel it out with some sort of an allocator. The nice part about having complete control of your memory allocation and deallocation is the opportunity for speed, right? So you can, for instance, have custom allocators for different kinds of objects. So the slab allocator, I think someone asked about that. So slab allocator basically says we're going to have different slabs that we use for different sized objects. Actually, that's not quite true. For identically sized objects, I believe. And so you might have here some pre-allocated objects of type foo. And if you want to allocate one, then all you need to do is go to find the first free one, possibly. But you don't, we don't have fragmentation because they're all the same size. So these things that are the same size will be here that we have to allocate a lot. Something else that's a different size will be here. So high-level language, and we're going to say that C is not a high-level language, will eliminate memory safety bugs, or eliminate a large class of the memory safety bugs. The idea, you have a garbage collector, and it automates the memory deallocation, right? So we've all used programs like that, or languages like that. Give me some examples. Java. Python. Did you say Haskell? Yeah. Okay, Haskell, yes. C#, yeah, many languages. Swift is an interesting beast on its own because it kind of, it does some reference counting to still not get you to avoid having to do freeze. So it doesn't have the typical garbage collector that others do. So yeah, and let's throw in here Go for some reason. Let's just mention that. Okay, so Go, Java, Python, etc. Okay. So convenient is not to be overrated. Convenient in the terms of you don't have to try and figure out who owns this piece of memory that this pointer points to. Really, to keep in mind who is responsible for freeing it. So if I want to share this among, let's say, multiple threads, I've got to keep track when the last thread goes away, who's going to get rid of it. And so it can be difficult and a source of not just bugs, but also using up your limited brain power in trying to figure this out. But there's a cost, right? It takes CPU cycles. It can delay execution, so we can have some latency issues where we might have a stop where nothing is happening and it's doing some garbage collection until we continue again. And it takes extra memory. Okay, in the days before concurrent garbage collection, this delay could be large, right? I want to go allocate some memory. There's no memory available. I will do a complete garbage collection, and then, milliseconds later, I come back and I give you your memory that you have requested. So safety versus performance, that is really the trade-off. And so what this paper wants to do is figure out what is the trade-off. How few people, not no one, but few people write OSs on bare metal with a language that has garbage collection. What are we paying? Right? And the takeaway from this is we're paying, what's the number? Around 10 to 15%. It's not an order of magnitude. It's not even twice. Right?
So when you're using a language that has concurrent garbage collection, does that mean the language spawns another process that does this garbage? How does it work?
So I don't know, let's pick something, Go. What happens, my understanding, is you've got your process. how hard is it to get pens? So we got our process, and the concurrency in Go is done with what are called Go routines. Okay? Think of them as threads. So by default, here's what happens. We have a Go routine, which is a garbage collector, okay? Concurrent garbage collector. And let's say we've got, user thread 1 and user thread 2 here. This guy is running along with these guys, and it's doing incremental garbage collection. And then as well, when you do an allocation here, right, of some sort, that goes into the garbage collection, and it does a little bit of garbage collection at that alloc time. Okay? So a little bit of whatever needs to be done so that all these are amortized, sort of over, the work is amortized across these alloc calls. In Biscuit, they get rid of this background thread. And so garbage collection only happens on an alloc. But it's not an all or not, it's not a stop the world garbage collection, it's an incremental garbage collection. So when I do an alloc, if there's lots of memory available, I don't do much. But if memory starts to be getting tight, I do X number of steps of my garbage collection. And then the next alloc, I do another X minus X steps, and another X steps, and eventually I'll have freed up memory. Does that answer your question?
So every compiled Go program, when you run it, it will spawn an additional Go routine along with whatever.
Along with the ones you have, yeah.
Original,
Yeah. That's part of the Go runtime that gets linked into your program.
Oh, I see. Okay.
So, yeah. It's not like Java where you've got this JVM, right, that you're running in. So some separate runtime, separate executable that you're loading your Java code into. In Go, when you compile, you get an executable.
Yeah.
Yeah. Okay. Okay. All right. So about 30,000 lines of Go. It's similar to Linux, and that's so that we have a good comparison. We don't want to have some special fancy fast techniques that we're using in Biscuit that aren't used in Linux, because then we're not comparing the effect of the language. Okay? And it has POSIX system calls, and you can run complex apps. So Redis is what, an in-memory key value store. How do we pronounce? Nginx. So yeah, it's a web server, load balancer, so on. Okay, so what happens? How is this actually organized? We've got our kernel. So I already said we don't have this special garbage collection coroutine. So we've got our kernel here. It's in Go, so we have Go routines. So this is a... What happened?
There's two more underneath the...
But there, oh, here it is. It's on the floor. And I'll put the bad one on the floor so that I'm not tempted to get it. So here we have a Go routine for process 1, a Go routine for process 2, and etc. All right? And so it uses the the switching between Go routines that normally happen as part of the Go runtime. Okay? So that's how we're switching between these Go routines. The context switch that happens there between a Go routine, Go doesn't know anything about page tables. And so page tables are not switched. So when you switch from process 1 to process 2, we don't switch the page tables. Before we go back out to user mode for process 2, we better switch the page table back to process 2's page tables. But while we're in the kernel, we can't use any process's page tables. Okay, so therefore, if we want to read or write memory into user space, we've got to figure out where that memory is and map it. Yeah.
Sorry, this is describing which kernel?
This is describing the Biscuit kernel. Okay, so just to reiterate, right? When we are in JOS, for example, when we're in kernel, in the kernel for process 1, our address space has the kernel right up in the top and has proc1 user address space here, right? And then when we are in proc2, this is proc2's user address space. In Biscuit, we don't have this part, okay? We just have the kernel space. And so therefore, if we want to go and read something from proc1's user address space, we're going to have to go find proc1's page table, take the virtual address, let's say they gave us for a write, figure out what physical address that is, map that into the kernel's physical address, right, assuming we have all of physical memory mapped in here. If we do, we can just go in and access it. If not, we'll have to set up a mapping to do it. Does that make sense? Go isn't designed to handle interrupts. So the problem is when an interrupt happens, it may happen in the critical section of Go, especially in Go's runtime. Like if you're in the middle of the garbage collector, it may be dealing with a critical section of updating pointers and so on. And so we can't, for instance, do any memory allocation in an interrupt handler. And in fact, we can't do much, and so all we do is just wake up a Go routine who's responsible for handling the interrupt. Okay, so we might wake up the disk interrupt Go routine or the serial interrupt Go routine, and then return. And then leave it up to the Go scheduler to see that this guy is awake now and can be scheduled and run it. And I believe they've tweaked the runtime so that it provides preference to those interrupt threads, Go routines instead of others. You had a question?
So the Go runtime has all these features like garbage collection, but it's also a compiled language. So when you, say you made like a hello world or something really small, when you compile it, does the binary have like, would it just be huge because it also has the Go runtime and everything?
That would be a nice thing to try. I don't know how big it is. Back in the day, that was a huge reason why languages like C or Pascal that had no real runtime were used to create executables. Right? Back in the day when a 100K application might be considered quite large, and it was very hard to have a program that also had a runtime that would fit in that. So that's practically why people didn't have, for instance, Common Lisp applications, okay? Because their minimal size was too large. These days, that's much less of an issue. But certainly, if you create a hello world in C and a hello world in Go, the Go one is going to be bigger for sure.
Sorry, can you just define what a runtime is?
Yeah, a runtime is our I should stay away from that. Our runtime is kind of our substrate that we're running on. So we have our Go runtime here. And on top of this, we have Go routines, right, which are just a fancy name for threads. Right? So our Go runtime is going to provide garbage collection. Okay? And as part of its implementation, it actually does have a GC Go routine too. So the Go runtime will have, let's say, allocation. So it'll have an alloc call of some sort. And the alloc call works in conjunction with the garbage collector and also has to work in conjunction with this Go routine to all kind of not stomp on each other's toes. And then the Go runtime also has to have the facility to be able to switch between these Go routines. How it's going to do that, I believe is going to depend on the operating system, right? So is it going to be using, so one example might be it uses a timer signal, right? And when the timer goes off, it gets a callback from the operating system, and then it goes through and chooses a different go routine. Or it could use thread primitives from the OS.
Isn't the whole point of go routines that it doesn't use any code primitives? Because they're lightweight?
If they're lightweight enough, then yeah, it wouldn't want to use that. It may be like Erlang that for sure doesn't use that. In which case, we're back to something like a timer. So I haven't looked at how that might. So it could very well be they're not using that. Okay.
Why do we need a separate go routine in the kernel for each process? Is this like an XV6 when we have like a separate thread?
It's like an it's exactly like XV6 where we have a separate thread.
Okay.
Yeah. So it provides us the context to run the ARM.
So can we think of a go routine like a process?
Think of go routine like a thread.
Go routine like, I mean, I'm sorry, can we think of a go runtime like a process?
Commonly, when you're running a Go program, a user program, this is all packaged together in one big process, right? It's in one executable, and when it executes, it's one process. Right.
But then the go runtime kind of functions almost like an operating system for
A very limited operating system.
the go.
Very limited operating system for the Go routines. A way to switch between them,
Yeah,
and a way to do garbage collection. That's it.
but the runtime itself has its own thread, like has its own thread of execution. It's not like
I doubt it.
how does it execute stuff?
Well, it's got a library, right? So where when you call alloc, that's sort of an entry point into this, and it can do things. And if it's set up a signal handler and a timer, then it's going to get jumped into when that timer goes off in order to switch between them. Does that make sense? So, all right. The biggest difference between Biscuit and Linux is handling out of memory. Okay, out of memory. So all operating systems face this. You have their kernel, some kernel operations allocate memory. When you open, it allocates a file object, right? Some sort of a structure with a file descriptor. When you call socket, it creates a socket object. And the user program is a control of when they're done with that, right? If they, for instance, close. So a user program can keep using multiple resources from the kernel. All right, which is, from the kernel's point of view, it's not that great, right? It's not a control of it. How can we, as an operating system designer, control how much resources a process uses?
I mean, you can swap things out to disk if they're using too much, or you can kill them.
You could swap them out to disk. The thing is, they are using space in the kernel, and so therefore, you'd have to swap out the kernel, their kernel data, as well as the user data. Yeah.
Just assign some upper bound on the amount of memory.
How many files should a process be able to have open? 256, maybe. Back in the day, it used to be 20. 256, I think on Mac OS, we've decided maybe is the default, and you can change that, to be tens of thousands if you want. But that is a control, one mechanism of control over how much memory a process can get created in the kernel on its behalf. So what happens if user code causes all the memory to be used? So you could have a malicious program or just a buggy program or a program that is deliberately trying to use a lot of, let's say, the memory, a database server that is, or a network server, that's open lots and lots of sockets. So the problem is if memory gets too full, then you get in a situation where no more allocations can take place. But if you're in the middle of some operation, like a system call, and you need to allocate, but you can't, what happens? Right? What do you do? In a system call if we can't allocate?
Fail if we know mem or something like that?
Fail. Yeah, fail seems reasonable, so fail. And actually, we got to maybe roll back, right? If we've done some previous operations, roll those back, and then return an error message, return enomem to the user, okay, to the system call. That gets to be a bit of a problem for some system calls, like exit. So what if you've got the memory hog, and the memory hog says, I feel bad about myself. I am going to die because I don't want to ruin life for everyone else. So I will call exit. And exit system call goes and says, I don't have quite enough memory here because I've got to close all these file descriptors and need to temporarily allocate memory. And so therefore, I will just return no mem. Right? So that's a bit of a problem. Linux's approach is interesting, I would say. So you could block in the allocator, right? That's one possibility. You're trying to allocate, there's no memory, you just wait until memory is available. What could go wrong with that? Okay, it could never become available.
I mean, in that exact situation you just described, whoever's actually using all the memory calls exit, and we block waiting for it to exit so that it can free the memory, but it is the thing.
Okay, that's true. It could be waiting sort of on itself because it's the one that's going to give up memory. Or I have a lock on something, and then I'm waiting for memory to be given up. And this guy who wants to give up memory is happy to as long as he gets his lock, right? So we can have this deadlock situation. So we could fail. And if you look at, for instance, the Linux kernel, you'll see that most all code that does a memory allocation, checks the memory allocation, and has an error recovery path to deal with that, where it will back out of whatever it's done and return a message to the user. Okay? There is this very odd thing, which is an unwritten rule called too small to fail. So too small to fail says, basically, if you do less than about 32K, which seems pretty darn big, will succeed. And there's code that's been written kind of to assume this. And it's really hard to change it to fix that. And even if you did fix it, you've got all these error paths through your code for dealing with a failed memory allocation, and it's hard to make sure they're right, because they rarely get executed. So there's just kind of this engineering problem in the Linux code base where they've got all of this code around that assumes allocations will succeed. So how do they do this? First, what they actually do is they do block for a little bit. They'll just pause a little while and see if memory becomes available. Okay? And then the other way to ensure that an allocation can't fail is to have a way to make a memory. So the way to make memory is the out-of-memory, I think it's called the out-of-memory killer. So the out-of-memory killer says, I wonder if I can find someone, some process, some lucky process, who I will kill and that will free up memory. Okay? And so basically they look at processes that have allocated a lot of memory and not use much CPU time. That is, they're kind of newer than older ones. And that will be the sacrificial process. And once that process gets killed, lo and behold, the guy who was waiting for a little while for memory to be available now will have memory available. It's kind of draconian, but that is how it is. Biscuit does not do that. Okay? So here's what Biscuit says. Sorry, I need to quit and come back to it. Okay, so Biscuit says, the problem with waiting on an allocation is that you may have a lock on something. But if you wait at the beginning of the system call before you've locked anything and make sure there's enough space to completely finish, you're safe. Okay? So we're going to block at the beginning of the system call until we have what we have calculated is enough space. No locks, therefore no deadlock.
Is this at all specific to Go, or is this something that could just as easily be implemented in C?
This could be implemented in C not just as easily for a couple of reasons. One reason is the general pointer arithmetic and so on that C has means it's hard to reason about a lot of things. The second, perhaps more important reason is that Go comes with a parser and scanner that'll generate an abstract syntax tree for your code, so that it's very easy to grab a piece of Go code and not compile it, but parse it so that you can then read it and see what's going on. And so that makes it easy to write a static analyzer that allows to figure out what calls are made, and so on. So we're going to do this static analyzer. It's going to do some analysis to get some ideas. If I've got this, the basic idea is this. So I've got some Go code. I've written like one piece of Go code, so I'm going to make it look like C and hope it's roughly the same, right? So this is Go. So I have a global. This is actually Go pseudocode. By saying pseudocode, I can make it look like whatever I want. Okay? You'll find when you do program, if you haven't already, code interviews on whiteboards, a lot of times they don't want you to use pseudocode because then you can make it do whatever, look like whatever you want. So if I have a global foo and I'm in func1 and I say foo equals new, object. Yeah, I'm really just making up syntax here. Okay. The lifetime of this object extends beyond func1. Right? Because it's referenced from a global. On the other hand, if I have func2 and I say local x equals obj. So this is just a nice piece of syntax. I don't have to say new if I don't want to in this pseudocode I just made up. So then if I say foo equals x, it's still used after this. But if I do stuff with with x, and it never gets assigned to a global, then I know when I leave func2, it's dead. I don't need that anymore. So the analysis is we have two kinds of objects. The type 1 objects are written to globals, and the type 2 objects only you get to from the stack. So the type 1 objects, we're going to presume they're always live. So we'll just sum those all together. The type 2 objects, we just have to look at every point in our call chain, what's the maximum set of objects that we have on the stack at any point in time. Right? So if func1 calls func2, and this is our entire program, then our maximum is one object in foo, plus we've got the y object within func1, but then when we go in func2, we've also got the x object. All right? Does that make sense? Now there's some work that has to be done to figure out these sizes. So there's some work like if you're dealing with arrays, well, There's just some work that has to be done, and there was some annotation that had to be done to the Go code. Like if you got a for loop that's running through making something bigger, how many times does that for loop run? We don't know. They just annotate it and provide a maximum, for example.
What if you don't know the maximum?
If you don't know the maximum, then we can't figure out how much space you'll use. And so we need a way to figure out the maximum. There are a couple of cases, I believe, where you could theoretically have an unbounded, like if you do a write with an unknown length, then they, like I think we did in XV6, cut it down to something manageable that we can actually deal with, okay? So that we make some progress on it.
Well, it sounds slower.
It could be, yeah. What else do we have to do? There are some cases where you have to cast pointers. And Go actually has a facility for that in their unsafe package. So the nice part is you know by name when you're doing something that's unsafe. Okay? And so about 90 uses, not a lot, really that many. So casting pointers, doing pointer arithmetic, things like that, you can't do without the unsafe package. I mentioned scheduling the interrupt go routines. So we want the interrupt go routines to run with higher priority than the non-interrupt go routines, and so they hack the runtime to do that. And counting allocations, and I'm not sure, I believe that has to do, if I remember right, with you figure out the maximum you're going to use, and then you start running, and it starts figuring out how much you do actually use. And then when you're done, you can, I think, unreserve that. I'd have to think more about that. So how did they use Go, right? What were good features of Go? Slices. What language has slices? Python has slices, right? So we have an array, and we can refer to a sub, where they have lists, and you can refer to a sublist. And it actually shares the storage for that. So that's handy. Deferring versus goto, again, not much of a Go user. This looked vaguely interesting. So defer allows you to say, I'm in a function, call this deferred function on your way out when you leave. So that's kind of handy. It's similar to in C++ using destructors, right? Or maybe a finally in Java. Closures, always handy. Maps built in, nice. Of course, the garbage collection. And the concurrent data structures especially, right? Who's responsible for what?
Wait, so what's the difference between just calling defer close file at the end of the function as opposed to just calling it like at the end of the function? Like, do you get what I'm saying?
If we have returns sprinkled through our function,
okay.
we know it's gonna happen
Okay.
in all those cases, in all those code paths. In Go, we don't have exceptions, so that's not an issue to deal with like we have in C++, where if we call a function and it has an exception, that we know our stack-based destructors will be called, because Go simplifies life. There are no exceptions. There are error codes, and you deal with errors. In order to do an apples-to-apples comparison, they had to make some changes to Biscuit, basically to provide some optimizations that Linux provides. So one example would be kernel text, right? Text is our actual code. And for the kernel, we, instead of using small 4K pages, use large pages so that we have fewer page table entries. And by having fewer page table entries, we don't have as much pressure on the TLB, right? Because any particular TLB entry that's referring to the kernel covers a lot more space. So we have fewer of them. The directory cache has this lock-free lookup where you don't have to have a lock. We'll be talking more about that next week. And nothing about Go prevented using these optimizations that Linux had. So it's not anything that's C-specific. So they took these demanding applications. They exercised them with a 10 gigabyte network interface controller, a TCP stack, virtual memory, and a file system. And when they're running this, basically, it's using up all of the CPU. And most of the CPU time is spent in the kernel, which is good because we're trying to see basically how much the kernel costs, what the costs are. So if we look at Linux versus Biscuit, there were a couple things that had to be done in order to make this fair. So Linux was faster, so with some optimizations. And so Biscuit added the optimizations. Okay? But Linux is also slower due to some features. An example would be, I think it's called address randomization, where when you load an executable, you randomly choose what address to put it into. Why is this good? What is this addressing?
Return-oriented programming attacks, I think.
Yeah. Any attacks on a program that rely on where particular code is in memory. Okay? So by loading it differently every single time you load it, you've got no one can attack this particular process by knowing where stuff is. Okay? So this is one example of the address randomization. And the nice thing is knowing Linux is probably just a compile time flag you use, right, to turn on and off.
I think it's changeable at runtime.
Even better, changeable at runtime. Okay, so there are some others here. And so these were turned off. Okay. So about 10%, of course slower than Linux, not faster, but about 10%. Garbage collection time, not that expensive, less than 3%. The cost of garbage collection is dominated by two factors. How many objects there are, right? Because you've got to walk object to object to object to figure out what's alive. And the second is, how much free heap do you have? Okay? Because if you have a little heap, every time you use it, you go garbage collect, and then free some, and use it and garbage collect, and use it and garbage collect. So the number of garbage collections is based on the amount of free heap. The cost of a particular garbage collection is based on how many objects you have. Okay? So Biscuit doesn't use garbage collectible memory for everything. Right? It uses it for most of the small thing. So there's an allocator for pages, for example, okay, which are used for memory pages, page table pages, the file content, the sort of stuff we deal with. So the page alloc type things would still be done with a page allocator and not using the...
So then now pages are not memory safe, so we can free a page twice accidentally.
Yes, we still can. We still can. But yes, we still can. So that is the trade-off. Then the other thing that they did was they actually took, for a couple of benchmarks, to make sure we have basically the same code path. So ping pong is a good example, pipe ping pong. So pipe ping pong are two processes that are reading and writing back and forth and back and forth. Okay? So it's like the ping pong you had in JOS, except instead of using IPC calls, it's using pipe calls. Now how can this work? Right? If I say, echo ls, pipe to WC, this is a pipe setup where the output of ls goes into the input of WC, right? How can I then pipe that back into ls?
Create a pipe that has a name and then pass it to both of them.
Could do that. Or just write a custom program that starts these up, right? Instead of creating one pipe and connecting the write end here and the read end here, I'm going to connect two pipes and connect the write end and the read end, and the other one, the write end and the read end. So this guy will be outputting this guy will be outputting this guy. I'm not going to actually use ls and wc, right? I'll just have, it'll probably just be cat, or something like cat might be what I'm using. Or I'll have just a custom program. So what it's testing then is pipes. Ping pong 15% faster, Linux or Biscuit?
Linux.
Yeah, Linux. Page fault 5% faster. The Go version has some safety checks. The other thing Go has is write barriers. So we talked about concurrent garbage collection and the fact that we have to keep track So let's just use the from and the to case. I believe they use a generational garbage collector, but that doesn't particularly matter here, right? So we've got our from and our to, and we want to know when we've got an object here which hasn't been scanned that we need to scan it to find all of the other references in here. And so in order to determine that, we have to know when we're accessing this. We could use page tables for that. That was one example we looked at. Instead, what happens is there's code that gets inserted to basically, as you access a field of an object, check to make sure what the status of this is, and if necessary, then scan it. So that's the write barrier, basically, that's there. Pauses are of importance, right? Again, we don't have stop the world. Right? Because that would be just awful if we had to wait, milliseconds, let's say, for garbage collection to happen. So this is measured, right? That the largest single pause was 115 microseconds. Now that's for a particular allocation. So this is one alloc. Because remember, the garbage collecting that's happening with Biscuit is only on allocations. So we're amortizing the cost of all garbage collection over each allocation. So for one alloc, we'd have 115 microseconds, but a particular system call may make more than one allocation. So the worst case they had was 574 microseconds across all of the allocations within a particular system call. So that means a system call could be delayed by up to this amount to complete. Now system calls can also be delayed because we stop before we start the system call and make sure we have enough space, right? And if we don't, then we wait. Yeah, in their takeaway was pretty good, and the performance is pretty good, but C is faster, yes. There are a couple of questions that came up, like, what about using other languages? So Python instead of Go. Dave.
So I still don't quite understand the previous slide why we would pause if we check beforehand that if we have enough memory.
Here's why. So we have calculated we have enough memory, okay? So we know the total allocated. We don't know how much of that has been garbage collected or not, okay? We don't know, so we've got our mem here. And let me just back up a second. So when we do an allocation, every time we do allocation, it may do some amount of garbage collection. Okay, some part of this incremental. It gets charged to any particular alloc. So when we do an alloc, we may have to pay for some garbage collection to do that, right? Even though we know that there will be enough memory for us to successfully get our allocations, we still are doing garbage collection sort of all the time, or at least when memory is roughly low. So there are two completely different pauses that happen. One, to wait until other stuff is finished, so we know there'll be enough space for us to run. And then the second is a fairly bounded time at every alloc.
So while we are running, that's when the incremental garbage collection happens.
That's right. While we're allocating.
While we're allocating.
Yeah, as we alloc. Yep. So a question came up, what about other languages, like Python? Python, multi-threading is harder, so it wouldn't be as useful a language. It's got this global interpreter lock where like all the world stops except the one thread that's running. I mean that's not quite true, but it has this heavy lock sort of contention. How does BISC access physical addresses? They use the unsafe. We talked a little bit about the Go code slower, so there's just more instructions. That's basically what it is. Okay. Does a reliance on different Go packages pose a larger problem when attempting to scale? I didn't quite understand this question. Relying on different, so I don't know that there's any reliance of anything other than the standard Go packages by Biscuit. And I'm not sure how this would pose a larger problem. So maybe the better answer is I don't know, because I don't quite understand. If you still have a question, come talk to me. Does a high-level language like Go increase the frequency or number of runtime errors that can occur? Yes. So if we have a out of bounds, we're going to get a runtime error. What do we do in the runtime error?
Panic?
Let's say we panic. Is that a fair thing to do? Whose fault was it? Let me ask you that. App developer, kernel developer. Out of bounds in the kernel. It's the kernel, right? Even if the app developer passed in garbage, the kernel developer is supposed to handle that, right? So it is a flaw in the kernel. We get a lot more information about it, and it's a lot closer to where it happened than it would be in C, right? In C, if we write off the end, when do we know about it?
Whenever someone wants to use that memory?
Yeah, it's like who knows when, who knows how much later on, and who knows how hard it is to find it. So there is a philosophy which is sort of fail fast, fail often, fail hard. I know at Google that was the idea for servers. If something goes wrong, just die. Okay? There were other copies of it that could continue running, but that one should die. And then there was also some special checks for, often these were queries, right, coming in from the internet in various ways, for what so-called queries of death, right? So some particular query that is hitting this bug and taking down server after server after server, and they would like carefully quarantine those queries and stop sending them. But then you would go debug why that happened. Why is Go statically analyzable? The basic reason, the most important reason I think was that it's built in. So that's why it's so common to create static analyzers in Go. And by built in, I just mean there's a Go package that has a suite of tools for dealing with this. Would less access to hardware cause some bugs to be harder to debug? I don't know that I would agree that Go has less access to hardware. I can't think of any.
Does Go have a mechanism to run inline assembly?
No, I don't. Not that I know of.
That has less access to hardware.
Because I have to make a function call? I guess access to hardware may require slightly more instructions, because I might have to make a function call. That's true. Type safety. It basically, you can't assign things of one type to another type. It knows what the type is. And unless you use unsafe, you can't change that stuff. The heap exhaustion, we talked about that. Why are C kernels popular, given that it's safer and easier? Because that's what people use. So Go was designed to be able to be used as a systems type language, right? Designed by whom? Designed by whom? Designed by who at Google? Designed by. Say that again? I don't think Russ Cox may have been involved, but there's this guy named Dennis Ritchie who was involved. And so, yeah. Oh, there's a shim layer. So this came up. So we've got the Go runtime. Right, and the Go runtime handles allocation and thread switching. Well, normally that relies on some OS primitives, right? But if you're writing an OS, you don't have any OS primitives. And so you write a shim layer, basically, that replaces this. That maybe has functions of the same name, like malloc or sbreak or something, but that work differently. Or maybe they just rewrite it, I'm not sure. I think they just make this shim to make it look like OS primitives. Yes?
What do you write that in, then? Is it like in assembly? Is it in... It's not in C. It's
Why not C?
You could...
Well, because they said they had no lines of C.
So all you really need to do is provide functions with the same name, right? So you remember how we have in JOS our library syscalls that look to your user program just like ordinary function calls and that actually implement using an interrupt, right? A trap call. Here, just replace ordinary functions with ordinary functions.
So we write our shim layer also in Go?
Yeah, we write our shim layer in Go. There's no C in Biscuit. There is some assembly, I believe. No, shim is, so a shim, how do we use a shim? Like if we're putting up I don't know, we're installing this. I don't even know what I'm installing, but I'm installing this and I need to, this is level, just like this. And so I put a shim in here to hold it up, right? So it's kind of an interface between two things. So shims are often used as something that right? We've got this code that expects a circle as input and kind of has a, let's say we make it like this, something like that. And if we want to put two together, then we can go like that, right? But if we've got something different over on the right side that looks like, I don't know, a square or something, then we want to put something in the middle that adapts the two. So this is a shim that will convert whatever this is expecting into whatever this is expecting. Does it matter to the user, library author, what language the kernel is written in? No. We have an interface. In the case of Biscuit, it's the same interface that Linux has. I thought this was interesting. For JOS, we haven't had to do much dynamic allocation and freeing. What's the big deal? Part of it is our operating system is so small, right? There's not much to it. So we move some of the allocation out to, for instance, file system server, or network server, and so on. But if you look at Linux, there's a lot. How viable would we write an OS in Haskell? I was going to say not viable, and then I looked. And so, yeah, there are a couple of Haskell OSs, and I still have to read a paper on that, which was pointed to. All right, that's it.